Okay, so last time we were doing past paper questions for the topic of gravitational fields. We'll continue with that where we left off. But before we do so, is there any question that anybody has from any of the last lectures? I think Hamna Rizvi, this is your first class? I think this is your first class. Yeah. Okay, so basically I'll be teaching you the A-level A2 physics course, and we have really we have covered the first topic, which was of circular motion. We did some of its questions, and then we did gravitational fields. We have more or less covered the theory part of the gravitational fields as well. We were now focusing on the past paper questions from the topic of gravity. The lectures, they are being uploaded on YouTube. The first few lectures, they have been shared. I'm sure that these last lectures, they will be there. But now it's recommended for everyone to enroll themselves in the course and get done with the fee and all of that stuff, and start taking classes on a regular basis, right? Try so that you skip as less classes as you can. So really just try to be present in all of the classes. But if this is your first time, for anyone who's first time in this lecture, the previous lectures have been shared. You can check them out on YouTube, Mega Lectures YouTube channel as well. That's where they have really been shared at this point, in my knowledge. The notes are also available on the website of Mega Lecture under this section of notes. When you go there, you'll find physics notes by Basil, and you can find the notes over there as well. I think we'll continue with these questions, right? And so I'm doing these questions in a way where I can explain explain the theory behind it as well, right? So the conceptual part, I'm trying my best to convey the conceptual part as well. So those who were present in the last class, they know how we're going about these questions. We're going to solve these questions. So you students are going to volunteer and help me deciding about the way of thinking for the problem, and then we'll solve them together. So Hamna, are you aware of gravity? Have you, not gravity really, but I mean the topic of gravitational fields in A2 syllabus? Have you gone through it before or anything of that matter? Okay, so I'll recommend you to go through the lectures that are also there on YouTube, so you can follow up. But we'll start with the problems, and we'll continue with these. And my goal will be to clear the concepts in the problems as well. So we'll cover most of the part of the theory in these problems as well. If you have any problem, if you're stuck anywhere, if you don't understand anything, feel free to stop me and you can ask me whatever part that you do not understand. So with that, let's continue. This is the problem that we were doing last time, right? Is there any question from anyone who was present in the last class as well? In what we were doing? Any problem, any question? Just let me know if there is no questions so that we can kind of continue quickly. Okay, no questions. Okay, all right. So this is the problem that we were doing. Can you solve this one step by step? You mean this problem that I have opened over here, right, Hasib? Okay, so from the beginning. All right, so we'll do that. So let's read the problem first. The problem is that we have a global positioning system, GPS, and it is used and it can be used anywhere on the Earth. Now, the GPS system is really where you have a number of satellites which orbit the Earth in a circular orbit at some distance, this much kilometers above the surface. So which means that above the surface of the Earth, if you can see my pointer, above the surface of this Earth, it is the satellites are orbiting at a distance of 2.22 times 10 raised to power 4 kilometers, and they are going to orbit the planet Earth in this circular trajectory, right? So we are asked to calculate the angular speed of a satellite, GPS satellite, in its orbit. So we want to calculate this angular speed omega of this satellite which is orbiting the Earth, right? Now, in part A, we really just found out the mass of the Earth, or we showed that the mass of the Earth is this thing. So we just have to use that mass of the Earth. And so the idea was that what is keeping this satellite in orbit of the Earth? Well, we know the force, there is some force of attraction between the satellite and the Earth, and that is given by Newton's force of gravity, Newton's law for gravitation, which is this Fg, gmm by r squared, where capital M is the mass of the planet, which produces gravitational field, and small m is the mass of the satellite, which resides or is in the vicinity of this gravitational field produced by Earth. Now, on the right-hand side, we can say that really this gravitational force is the cause of the centripetal force on this satellite. So this force of attraction is causing this satellite to remain in this circular orbit around the Earth. So this point, circular orbits, was a key point, and that's the reason that I can say that the force of gravity is equal to the centripetal force, because the force of gravity is the cause for that centripetal force to be there. So is that clear? All right. So if that's clear, I have this problem seeing chat every time. If it's convenient for you, it would be better if you can unmute and just let me know, right? Otherwise, I'll have to keep looking into chat from my PC. But anyways, okay. So we know that the force of gravity is really capital G M m by r squared, and the centripetal force in terms of angular velocity is given as mr omega squared, right? Where this m is really the mass of the satellite, because the satellite is really in the circular orbit, right? So small m is the mass of the satellite. Now we can simplify this equation and write it for the angular speed. So you can just cancel this m with this m, and this really becomes omega squared is equal to g m by r cube, right? So that's the equation that you would have, and then you can just write it as omega equals square root of g m by r cube. Now we have everything. We have the mass of the Earth, that's there. The position of the satellite from the Earth is also given. So we'll just put in the values over here, and you can find the value for omega. So this is just 6.67 into 10 raised to power minus 11. That's the value for G. Mass of the Earth was 5.99 into 10 raised to power, what was it, 24 kilograms, right? We found that in this part. and it's also given in this thing. So we just had to show it. So even if, for example, the student was not able to do this thing, he would still have the mass of the Earth, so he would not fail in this second part of the question. Anyways, so that's that, and then divided by, now what would be the value of R? It would be the value that how much further away is the satellite. So how far away is the satellite? It's 2.22 times 10 raised kilometers. So what value would I use in R? Anyone from the class? Can you hear me? I think, are you using chat? No. Okay, you can hear me?
2.22 into 10 to the power of 7.
You're saying it should be 2.22 into 10 raised to power 7. Okay. But that's the rate, that's the distance that the satellite is away from the surface of the Earth. Do you think, don't you think we should?
The radius?
Yeah, exactly. So we need to add the radius as well. So the value that I'll use over here is simply this 2.22 into 10 raised to power 4 kilometers plus the radius of the Earth, right? And remember, this is kilometers, just converting it into meters is 10 raised to power 7, and then use the radius of the Earth in meters as well. And the rest is just a matter of putting the values in a calculator, right? So that's, everyone agrees with this? Is it understandable?
Fixed value, right?
Sorry, can you repeat?
The radius of the Earth, it is a fixed value, which may be
the radius of the Earth is a fixed value, right? Exactly. It was 6,400 kilometers, right? I think, if I'm not wrong, it was 6,400 kilometers. It's a constant, really. Yeah.
Sir,
so
it's just an approximate, so it's not important to like memorize the value, right?
Sorry, it's not important to what?
Like it's an approximate value, the radius of the Earth. So is it important to memorize the value?
Oh, no, it's not really. I think the value is given in your formula sheet. You have two, I think there are two sets, right? Where you have, in one part, you have all the values of constants, and then you have some of the formulas as well. So in the section where you have all the constants, radius of the Earth and mass of the Earth, I think as well, they are given. So you don't have to memorize this, the radius of the Earth. Right, so any other question from this thing? You'll just find the value, put this in the calculator, put the values, take the square root, whatever answer you get, just write it over here. Make sure that your units are aligned so that you can get the answer in radians per second. So you'll have to convert your kilometers to meters, and well, that's the only conversion that you have to be aware of in this part. So is that clear for everyone?
Yes, sir.
All right. So for everyone is okay with this thing?
Yes.
All right. So then we can move on to the next part. Okay, so here he says that use your answer in part 1 to show that the satellites are not geostationary orbits. So we have to show that the satellites are not geostationary orbits. Okay, so Can someone very in a quantity that can mathematically describe geostationary orbits? Can someone explain or just tell me what that is? How do I define geostationary orbits using a mathematical expression?
If the satellite is not the speed of the satellite is not equal to the speed of Earth revolving.
You're saying then it would be not a geostationary orbit.
I guess no.
Yeah. So if the speed is not equal, so or you could also think in terms of the time period, right? So if the time period is not 24 hours, then it is not geostationary. Geostationary really means that the time period of the rotation of the Earth and the time period of the rotation of the satellite is equal to the time period of the rotation of the Earth, right? That's how we defined geostationary. Any object that is lies in a geostationary orbit. So your thing is also correct, because the period of the orbit is really defined as 2 pi by omega. So this we can find it in terms of this angular velocity, and if the time period is not equal to 24, then we can conclude easily from that that the satellite is not in a geostationary orbit, right? So everyone agrees with that?
Sir,
Yes.
what will we take T, or do we have to find T in this case?
Oh, we have to find T, right? So we will get we from the previous part we found the value of omega, which I did not put the values in a calculator, but let me just quickly check what you get so I can also use this in the time period. Okay, so give me a second. Okay, so it's around about 1.3 times minus 4 radians per second, right? So this is the value for the angular speed omega. So I can just use now this value. I'll use it in this omega. So this really becomes 2 pi by what was the value again? It was, I think, 1.3 into 10 raised to power minus 4 radians per second. So this radians goes with this 2 pi radians, and second this comes up, and the 1 over this thing is really it's 4.8 into 10 raised to power 4 seconds. If I convert this into hours, that is just, you'll divide this by, first you'll divide it by 60, and then you'll so you'll get 13.4 hours, right? Now the answer to this time period for this satellite is 13.4 hours, which is obviously not equal to 24 hours. 24 hours is defined as geostationary. So this thing is not equal to 24 hours, hence it is not geostationary. So that's the answer to this thing. So is that clear for everyone? I cannot hear you. Is this thing clear?
Yes, sir.
Okay, it's okay. Amazing, great. Okay, so you guys are using chat box, but actually I cannot really see the chat box in here. I'll have to keep checking with my PC, and it does not give me any notification as well, which is weird. But so that's why I always ask to use the mic, really. Okay, so if this is clear for everyone, right? Alicia, Anna, Hamna, and Hasib.
Yes, sir.
Yes, sir.
All right. Okay, great. So Then we can move on to this next part, which says, okay, so you'll have to think in this thing, right? The planes of the orbits of the GPS satellite in the part that we just solved are inclined at an angle of 55 degrees to the equator. So this is the Earth, and wherever the satellite orbits, it's going to really, there, you can draw it as a plane, and this is a plane in which the satellite is orbiting, and this plane is really inclined, where this thing is the equator, right? This thing is the equator. The plane is inclined at an angle of 55 degrees to the equator, and this is where the satellite is orbiting. So this thing is the satellite, and it lies in that particular plane, and it's going to orbit like this. Now, they're asking you why the satellites are not in the equatorial orbit. So they're saying that why did I not keep the satellite plane at an, you can say, a 0-degree angle to the equator? So like, why is it not in this plane, the plane that is on the equator? Why is the satellite not here? So can anyone think of a reason why should the satellites be at an angle which is kind of above at this side of the Earth, and then it orbits? It's really, the satellite is really orbiting in, if it's like this, it's going to, this circle that I drew, it's not really an accurate description. You'll have to imagine it. If it is inclined at an angle, it's orbiting throughout this Earth, right? All the way around this Earth. So you'll have to think about this. Why do you think the satellites are not, it's not preferred to put our satellites in the this orbit, which is lies at the equator? Because if I put these satellites in this equator, they kind of just cover this part while orbiting. Why do I put them in this thing? So they are going to really, this new circle that I drew, let me just use this thing, this one with a blue, light blue line, that's really the orbit that would be really followed by this satellite if it's in this inclined plane. So why do that? Why not do this in the equatorial orbit? Why not do that? Anyone? You can feel free to guess, take a guess, even if it's wrong. Who cares, right? No one is judging you over here. Just think about it. That's what I want. And come up with your answers, reasons why could that thing. Anyone from the class? Hasib, what do you think? Why is that the reason? Why is the satellite not preferred to orbit in this way, but rather in this way? Think in terms of what's happening. What is the purpose of this satellite really? The satellite is kind of providing information of the Earth, right? So if the satellite orbited in this way, what information would it be lacking really? Imagine that you're sitting in the satellite and you are observing the Earth, but you're orbiting in the equatorial orbit. There is some part of information that you would not receive. What could that be? No idea, no guess. You can just say anything, but okay. So I'll let you know. Okay, so think in terms of the. I gave you a very big hint as well, that you should think in terms of what is the purpose of the satellite. So satellite has to record what's happening on the Earth, right? So it's really, if, for example, climate change or whatever, right? Now, if the satellite is in this orbit, then it really cannot see what's happening at this point, at the top point of the surface. And it also may not be able to see what's happening at this point. But if it's in this orbit, which is inclined at some angle, then it can cover every part. It will cover the what is happening at the poles. It will cover what's happening on these sides and everywhere. It can also cover what's happening at this south pole. So the reason is really that the satellite is inclined at this angle so that it can provide an entire coverage of the Earth, really. And you can say that while it was in the equatorial orbit, it was providing some cover of this side of the Earth, but it could not provide any coverage of the poles. Hence, the satellite is placed in this orbit where now it can provide the entire coverage of the Earth. So hence the poles are also included when it's orbiting it in this way. So does that make sense? Is that clear?
Yes.
Okay, so it's clear
Yes.
for everyone? Okay, great. So that's the reason. So you can just say something like, the question was why the satellites are not in equatorial orbits. So you could say something like, as they would not provide a coverage at the poles, right? So it was just a 1 mark question. It was really just actually I thought of this question as an interesting one because it promotes thinking, and so that's why I kind of spent a bit time on it as well, even though it's just a 1 mark question. But yeah, so I hope it's clear now, right?
Yes, sir.
Okay, great. So we can move on to the next question 3 that we have over here. And the question states, define the gravitational potential at a point. So anyone willing to answer this thing? What is gravitational potential? How is it defined at any point?
The work done per unit mass and bringing a point mass infinity, I think.
Yeah, exactly. So it's really just the amount of work that you have to do. So it's just the work done in really moving a unit mass from distance that is very far away. So basically, so those distances we refer to as infinity, right? To a particular point in space. So that's the gravitational potential at a point, right? In to a particular point in space. I forgot to write point, so just put it. So that's clear for everyone, right? Yeah, I gave an idea of what gravitational potential is while we were covering the theory part of this. So you just have to remember what it is, and then you can write it in your how the understanding of the you can write over here. So that's clear for everyone.
Yes.
You can assign this a specific field, gravitational field potential point in space, really. Okay, all right. So that was just the definition. Then you have the Earth may be considered to be an isolated sphere of radius r with its mass concentrated at its center. A statement similar we have encountered before as well. So I'll not go into the details of what it means. The variation of gravitational potential with distance x from the center of the Earth is shown. So we can see this graph, but whenever you look at these graphs, first of all, just remember to make sure that you read what is on the y-axis and what is on the x-axis. So you should, of course, you can tell that this is the potential and this is the distance. That's not really what I'm talking about. I'm talking about these things where you see that this is given in 10 raised to power 7. So any value over here it really means this is 4.0 times 10 raised to power 7 joules per kilograms, right? So that's something important. So remember always to check this thing on the graphs. So here we can see that this is the potential, and we're given the potential at every for some radiuses. We can see that at the radius r of the Earth, it's some value you can see from this thing. It's just this value. And similarly, when the radius is 2 times the radius of the Earth, so you're moving away, and so the value of the potential starts to increase, really, right? So everyone agrees with that? The potential is increasing. As we move away from the Earth.
Yes.
All right. So you're given the radius of the Earth as this thing. And apparently the question that they're asking you is on this next page. By considering the gravitational potential at Earth's surface, so at Earth's surface, what value of distance should I use? It would be r, right? So I'll use the gravitational potential at r, this one. So is that clear why? Because of course the at the surface the distance is r.
Sir, what will be the potential at the surface?
You'll just so you'll look at the value of r in this distance, because at surface of the Earth the distance is just r, right? The radius of the Earth. And so you'll just go down from this r like this. You'll go down like this, and then you'll check on the y-axis. It is this value. Now you can just make a guess. If this is 6, this could be 6 point. If you want to make an accurate guess, then this could be -7. So this would be something -6.3, right? -6.3. And don't forget this into 10 raised to power 7. So if I have to write the potential, the value of phi at r is really -6.3 into 10 raised to power 7 joules per kilograms. So that's the potential at the surface of the Earth. So is that okay for everyone?
Sir, which formula will be used for this one?
Oh, we just okay. So I think I should have mentioned this as well. On the vertical axis, we are given values of potential, and on the horizontal axis, we are given values for distance. So because at the surface, really implies that we are talking about when the distance is just equal to r. Now, if we know that at the surface the distance is r, then on this horizontal axis I look for this r, where now I see r is over here, and now I'll just go down vertically where this meets the curve, this curve that you can see over here, and then just go like this horizontally towards the potential axis, and then read off this value, because this value is value for potential. So we're just reading the value of the graph, right?
Yes, sir, I get that, but I was asking which formula will be
Oh, sorry, you're asking?
find mass.
Oh, yes, of course. Sorry. Okay, so that's what you're asking. Of course, we are. I was just clearing this thing out. So this is okay, right? So this value of phi is everyone agrees to this value of phi in this class right now, right?
Yes.
Everyone agrees with this value of potential.
Yes, sir.
All right. So this is the value that we get for that we use the graph to find this value for the potential. Now I'll just take this value and let's take it back over here. 1 second, paste. Okay, here it is. So this is the value that we obtained from the graph, and we have to use this value to determine a value for the mass of the Earth. So we know phi is equal to what? Phi is equal to gm by r. So everyone agrees with that, right? Or is there something else that I need to have in this expression?
The negative sign.
Exactly. So there should be a negative sign with this thing. Okay, so great. Now we need an expression for m, so we'll just rearrange this. Nothing too fancy. We just get this thing as minus phi r over g. Now we'll put the value. So we have this minus, which comes from here, and then we have a minus in this value for phi, which is minus 6.3